Hello physics friends, welcome to the start of a new chapter. Mr. Collier here, and today we are going to talk about work. Work in physics has a very specific definition. It is the product of the force exerted on an object and the displacement of the object when it moves in the direction of the force. So basically in physics you're only doing work if you apply force to an object and it moves. That gives us a new equation, work equals force times distance. Now, work is a scalar quantity, but we are still going to make it positive or negative based on the direction of the force that's applied. And this is because work does relate to adding or removing energy, so we are going to play around with positive and negative work. We can represent work on a graph by looking at the area under the force versus displacement curve. Since work is force times displacement, if you have a graph that has force and displacement, the area under the curve will represent the work done. The unit for work in the SI system is the joule, named after a scientist, James Prescott Joule. A joule of work, represented with a capital J, is the amount of work done when you apply a 1 Newton force and move an object 1 meter. Now that's actually a fairly small amount of work, and it's actually the same unit we're going to use for energy. So a joule, as you'll find, is going to be a fairly small amount of work or energy. Now let's look at how this might show up in some problems. A couple simple ones here. We'll get into some more complicated ones in class. What is the work done by me on luggage, that's 10 newtons, to lift the luggage 0.5 meters? So one thing to consider as you're answering these questions is the language. We're going to see what is the work done by me on the luggage. What is doing the work is an important piece of these questions. That'll show up more in our homework. So work is going to be force times displacement or distance, and we've got a 10 Newton force applied over 0.5 meters. That's going to be 5 joules of work. Now, what happens if I lower the luggage 0.5 meters? You'll notice that the main difference here is the direction of movement is in the opposite direction. So we have a negative work. Now, a little comment here that force opposite of the displacement is 180 degrees away from the displacement, and the cosine of 180 is -1, so it's negative work. That's going to show up in just a second here as we define work as force times the cosine of the angle between it and the displacement. So what would be the total work done by me on the luggage? Net work is the sum of all work done. So in this case, 5 joules up and 5 joules down gives me a net work of 0 work. So from a physics standpoint, lifting something and putting it back where it started is not actually doing any work at all. A couple key things that will come up as you work through this chapter on work. Objects that are at rest may have forces acting on them, but there's no work done on the object if there's no movement. You can push against a car that's stuck in the mud as hard as you want, but if the car doesn't move, you haven't done any work on the car. Also, the work done by a force needs to be in the direction, needs to cause the object to move in the direction of the force. Now, if the force and displacement are not in the same direction, then we need to consider what component of the force is in the direction that we're concerned with. So we're going to be using cosine, right? If you look at this little diagram, we've got an angle here, and this is adjacent to the applied force, which is this right here. Since it's adjacent, we're going to be using the cosine. So for example, the work done in the moving carrier as it moves it 3 meters to the right by a 40 Newton force at an angle of 35 degrees is going to be the applied force, 40 newtons, times the cosine of the angle, 35, times the distance that it moves. And that'll give me my answer. Now just a reminder, since it's force times displacement, a Newton meter is the same thing as a joule. Now so far this year, all of the stuff that we've been looking at has been constant acceleration, constant forces, and things like that. Robert Hooke realized that a lot of work done involves forces that are changing over time, and he came up with a relationship to describe that. This relationship is known as Hooke's law. We're going to look at a very specific example of it. If you get deeper into physics, you can go deeper. But what we're going to look at is springs. What he realized is that as you apply a force to a spring, whether you're stretching a spring like this diagram, or if you've got a string that's stretched and you're compressing it, that as it stretches or compresses, the amount of force that it takes to continue stretching or compressing it changes. It's proportional to the distance. So like stretch it more, it gets harder to stretch. And so if you graph that, he realized that there's actually a graphical relationship here. And he came up with the slope of that as the relationship K, which we're going to call the spring constant. Spring constant is measured in newtons per meter, and the stiffer the spring, the higher the spring constant. In other words, the more newtons it takes for every meter that you're stretching or compressing that spring. And so that actually gives us a relationship here that the force that a spring applies is equal to the opposite of the spring constant times the displacement. And the reason it's the opposite is because when you apply a force, the spring applies a force in the opposite direction that you're stretching it. It's trying to get back to where it was. So if we look graphically at Hooke's law one last time, this is going to be true for ideal springs, but we'll find that when the elastic limit of the spring is reached, it's no longer valid. We're going to try not to do that because that's what ruins springs. But let's derive one more equation here and then we'll wrap up. So work is the area under the curve, so we can actually rewrite this to kind of calculate the work under the curve. And now the work under the curve, since it's a triangle, is basically 1/2, and we can derive a new equation from that. Work is equal to 1/2 of the spring constant times the displacement squared. So we can actually figure out how much work is done as you're stretching or compressing a spring. So, in summary, we've got two new equations. We've got the spring constant equation here, and we've got work equals force times distance. We learned a new unit called the joule, and we are ready to tackle work. We're going to see next how it relates to energy. Good luck.